Alright, looks like we're live. Hello everyone and welcome to yet another Azozin session. How about that? Bet you didn't expect that shit to happen. Hello. Why is this a GitHub? Like, autocompletion actually screws me up all the time. Hello, hello, hello. Let's make a little bit of an announcement on our Discord server. Right, so live, I mean it's actually red. Circle live on Twitch. And what are we doing today? Today we are implementing a prefix tree in C. That's right, that's what we're doing today. And the reason why we're implementing a prefix tree in C is because I always wanted to, right? So I'm in the middle of like working on Porth and just rewriting Porth from Python in Porth. I just wanted to stream something, right? And I looked at the list of the topics that I have, and one of the topics I found there was the prefix tree. I always wanted to implement a prefix tree. Hello everyone, hello and welcome to another Zozin session. So hello Iguduk, hello Bitstream, Kami SMB, Ocamel, Nihilete, Bitstream, Lvev7, Smir PGPJ, hello, welcome. So the question is, what the hell is a prefix tree? That's a very good question, so let's actually Google that. So prefix tree, so maybe we're gonna take a look at the Wikipedia page. So it's actually called tree. In some sources, sometimes it's called radix tree. I don't know who should I believe, but we're gonna actually like go with tree maybe, but I'm gonna call it prefix tree throughout the stream. So here is an interesting thing. I know nothing about prefix tree. In fact, I read nothing about the prefix tree. Prefix tree. So maybe I'm gonna do it like this, Wikipedia article about prefix tree. So I'm gonna put the link to this thing in the description for anyone who's interested, and I'm gonna actually post that in the chat as well. So I00 Alan, thank you so much for 2 months of Twitch Prime subscription. Thank you, and welcome to our epic Prefix Tree Club. That's right, so we're Prefix Tree Club. So here is an idea of prefix tree. So I'm gonna go off of a single image, right, about this data structure. I'm gonna go off of this specific image. So the idea is basically you have a tree and you build it by going through the characters of the words. It's kind of difficult to explain. Maybe I should actually try to draw that. We have a lot of subscriptions right now. Droka87, thank you so much for 7 months of Twitch Prime subscription. Thank you, and welcome to our epic prefix tree club. And Jordana BC, thank you so much for tier 1 subscription, your first subscription by the way, and welcome to our epic prefix tree club. Alright, so let's actually try to draw this shit. I think it's going to be very useful to at least try to draw that. So imagine that you have, I don't know, something like, for instance, word hello, right? So let's actually try to write a word hello. Hello, right. So, and essentially, you're going to have the following tree. You're going to go through the characters from left to right. And for each character, you're sort of going to build a node, right? So here is the root. A root doesn't contain any characters. So for H, you're going to create an edge. So here is H. Right, so here is H. And this is where H lives. So here's H. Then you go to E and you basically branch off like this. So for each character, as you can see, you create a separate node and you continue until you finish the entire word. Right, so the next one is going to be L. So this is basically L, and then we're going to have a second L. Here is the second L, so it looks like B more, like this is actually L. I'm trying to make it look like L. And then you have the sort of like O, and here is the O. Right, so here you build like a part of the tree, a subtree for this specific word. Right. So then, for instance, like you want to add another word in here, right? But it would be nice to actually have an example that has like a common prefix with hello, right? So it will be actually kind of cool to have that. So what has a common prefix with hello? I don't know. So maybe something like helium. I think it's a pretty good example. Yeah, helium. So because they all both start with HEL. Right, so it's going to be helium. Right, and you basically repeat the process, right? So you see H, you go to the H, then you see E, you go to E, then you see L, you go to L, right? And this is where it starts to deviate. The next thing you see is I, so that means you branch out to something like I. Here is the node for I. And then you continue, so there is a node for U. Right, so this is the new node, and there is a node for M. There we go. So, and basically you have a bunch of words and you add all of these words into that tree and you build like tree of prefixes, right? So, and at the ends of the words, right, in the leaves, you can store some sort of a value, right? Some sort of a value associated with that specific prefix, right? And it makes it super easy to find that value in the tree in O of n, where n is the length of the key, right? So it's almost like hashing, right? So if you have a hash table, you only need to like compute the hash of the string, and then you can quickly find this the value in O of 1. So in this particular case, you just go through each individual character and you go this path and you find that value in there. So what's interesting is that you can also use this data structure for autocompletion, right? For instance, you have a particular prefix, right? You typed HEL. Right, and then by following that prefix, you found a subtree, right? And then by doing a DFS on that subtree, basically traversing all of the possible paths, you can find all of the possible autocompletions for that specific prefix. This is at least how I understand the prefix tree works. I never read any papers on the prefix trees. I never actually implemented it myself. I only looked at this picture. So everything I just explained, I derived by looking at this picture, right? And I want to try to implement that data structure only using the knowledge I derived from this specific, image, and see how well I'll be able to do that. So it's kind of like a sort of a challenge. So, and that's going to be the topic for today's stream, right? So let's just see how you can implement something like that in C. Sounds good? Sounds Gucci? Sounds Tamaguchi? Let's go. And maybe then we can even implement some simple autocompletion, right? So maybe we're going to build like a tree out of the source code of the implementation of the tree, and then build a simple app. Then when you start typing something, it will just try to autocomplete something. Right. So let's go ahead and freaking do that. Hopefully that makes sense. Alrighty, so I'm gonna close my paint, then I'm gonna close everything in here, and let's start. So I'm gonna go to my folder, to my trusted Zosian folder. I'm gonna create a prefix tree. Do I already have something? No, I don't. Alright, so prefix tree. Okay, let's create a C file, and let's implement a hello world, right, to get things started, right? I usually start with a hello world, just to test things out. Right, and let's do something like hello world. There we go. So next thing we want to do, we probably want to implement some sort of a building script. So let's actually open build.sh. right? So it's going to be in sh, and then in here I'm going to just do something like cc WOWR. That's definitely something that we want to have. The standard is going to be C11, and we're going to be very pedantic about it. Pedantic, and then we're going to also enable all of the debug information, right? So maybe I'm gonna call this entire thing tree, right? Don't really want to call it main. Let's call it tree. Do we need any libraries? I don't think so. I think that's everything that we're gonna have in here, right? So, and then I want to move main.c to tree.c, and then I'm gonna make the build executable. And I'm gonna just run it, and it built it, but didn't print anything. One of the things I like to do, I like to enable the tracing and the errors. So basically X in here makes it so each command in a script is going to be printed, is going to be echoed when executed, and E means that if any of the commands fails with non-zero exit code, it will fail the entire script. For some reason, by default, this is not a thing in shell scripts. I don't really know why, because like in many situations, in 99.99% of the situations, I want to enable E. Right, that's what I want. If something fails, I really want it to fail. If I don't want it to fail, I would probably wrap it in if statement, right, and handle it myself. So, I don't know, maybe it's some sort of like a leftovers from old times or something like that, I don't know. Anyway, so as you can see, it builds everything and it prints everything. So we can do something like tree, and there we go. Here we have a hello world. How about that? How about that? We're already 10 minutes into the stream and we already have a hello world. That's freaking amazing. That's very, very productive. That's already more productive than an average Java Enterprise Edition developer. So we implemented how many lines of code did we implement? Oh my god, I can't even open anything. So we implemented like 7 lines of code, right? So for an average Java Enterprise developer, that takes around a week to implement, going through all of the research and then review process and shit ton of meetings and stuff like that. So usually they write 7 lines of code in like per week. So we managed to pull that off in 10 minutes. So that's how productive we are. So anyway, so let's continue. So the thing we need to do, we need to implement like the node, right? So since we're building a tree, we need to define a node. Right, so let's go ahead and do that. So struct, this is going to be a node. Something is really weird in here, right? So here's the node, and if I understand correctly, so maybe I should actually open the the thingy in here, the tree, so I can have this picture in front of me. So I suppose in the node itself, we're gonna store the character. Oh, here's an interesting thing. This is not a binary tree. You can't just do some shit like let me try to find it. So it's gonna be tree prefix tree. So this is a tree.c. You cannot just do something like node left, right, and node right, because it's not binary. So you can have a lot of children. So it's more of an array of children, right? So something like this. So maybe we're gonna do it like this: children. And so the amount of children apparently can vary, right? Because not from every character you go to other character. So I suppose you want to have something like this, right? Children size, which is not particularly convenient. Right, and then you're also gonna have some sort of a character in here, right? That indicates what kind of node it is. But then you have to think about managing the memory for this like dynamic array, right? So, but here is an interesting thing. If we're talking only about something like ASCII, right? If we're only talking about something like ASCII, we're probably not gonna have more than 256 characters, 256 children anyway. Right, and you know what we can do? I think we can do something like a fixed amount of children, right? So we can have array of pointers, and if there is a child for that specific character, it's not going to be null, right? So essentially, if you have something like this, like a root, and you want to see, does it have a child for a character A? So you can do it like that. You can use a character as an index in the array of children. That's very convenient. That is actually very convenient. So, and the size of the structure is going to be rather big, right? 256 pointers is like, let me see, it's Python 8 multiplied by 256, 2 kilobytes, right? But we are living in 2021. Memory is cheap. Memory is freaking cheap, so I think we can afford 2 kilobytes per character. Anyway, so I think we can afford that. At least we're only learning, right? We're only learning. I'm implementing this data structure for the first time. I don't really know what I'm doing. I'm just exploring things. And as we explore, I think we can allow ourselves to allocate 2 kilobytes per character, all right? So though there are ways to, you know, decrease that size, right? Because we probably only care about the displayable characters in ASCII, right? And the displayable character range is actually smaller. And on top of that, we're probably not going to have all of the possible combinations of all of the possible characters. So we probably don't need 64-bit addressing. We can actually use smaller pointers, right? So essentially we can have something like a node pool, right? Node pool, which has a limited size. Let's say node pool capacity and something like, maybe it's going to be even dynamic, right? So node pool capacity, let's say it's going to be like 1,000 of them. And essentially, instead of 64-bit pointers, we can use 32-bit indices. So we can, instead of 256, we can use a displayable range which is smaller, and instead of 64 bits, we can use 32 bits. And maybe if we know exactly what kind of data we're dealing with, we can use even 16 bits, right? So it's going to be 65, 65,000. Right, but it cuts down the size even further, right? It makes it even further. So there's a lot of ways we can, compress this kind of stuff, right? So maybe if the data that we're dealing with is like super small, we can even have it like this, right? So essentially what we're doing here, instead of like absolute pointers, we're using relative pointers, and they're relative to some sort of like a node pool. So we're not going to implement it like that right now, right? I'm just exploring different ways to, just trying to see how much room I have in terms of like compressing the memory footprint. And to be fair, right now I don't really care about memory footprint. I just want to see what I can do, right? If I need to care about it. So here's an interesting thing. Since the character is determined by the position in the array, do we really need to store the character in the node? If you have something like root, right? So you have a root, and for instance, you find a children for character H. Then to find a children for character E, you have to get this. And then this, like, you never have to like look into the character of the node itself, right? So the actual characters are determined by the indices within that array. So basically, we don't need to store anything but children, and maybe the occasional value, right? So maybe the value that is associated with that specific key. But right now, I don't really want to implement any like a dictionary or any associated like array. I don't want to associate strings with values. I just want to build that tree so we can do autocompletion or something like that. So because of that, our node is going to be basically a structure with 256 children. That's actually pretty cool. It's pretty straightforward, and yeah, I really like that. I dig that. It's pretty cool. And since we already like allocated the sort of node pool, let's actually go with the node pool. So we're gonna have our custom allocator, right? So we're gonna have a fixed region, and we're gonna allocate the nodes within that region and never free that, right? Because who cares about memory in 2021? If it's good to know if the node is a leaf. I guess if you are storing values, but I don't want to store values in there. I don't really want to store values. I just want to store the things. Exit is better than free. I do agree with that. Like, I don't understand why people are so obsessed with freeing things, because operating system is gonna free everything for you, right? You know what's even cooler? Like a reset button. It like frees everything. Anyway, so let's continue. Okay, so node pool, and let's actually have something like count. So we're gonna keep track of how many nodes we allocated within the node pool. And let's write a simple allocator, right? So let's do something like alloc node. And this thing is going to just like allocate a single node within that region of memory. Okay, so what do we want to do? We want to first check that we even have enough nodes to allocate. I could have made it like a dynamic array, but I don't really care right now. So let's actually make it fixed. Right, so right now what we want to do, we want to, you know, implement something working. So if node is greater or equal than node pool capacity, maybe I want to actually do assert, right? Actually want to do assert because I don't want to, you know, handle this thing properly. Isn't that something we discussed in the Discord server recently? Yeah, somebody posted in our Discord server a thing, like a justification of not having assert in Golang. And the justification is very interesting. So basically it encourages people to not handle errors properly and just stick assert into it. But for the servers, right, the very thing the Go was designed for, it is very dangerous because servers should never stop and you should handle all of your errors without stopping the server. But here's an interesting thing. It never stopped people from doing something like this, where if error not equal nil, panic, which is not that longer than, you know, maybe assert. It's just like a little bit longer. So, and people still do that anyway, so they didn't really achieve their goal. So, because clearly this is something people want, right? So clearly this is something people want, and just like you can just easily, you know, force a particular mindset on people. So anyway, and we're not developing server anyway, so who cares? So let's go ahead and do node pool, and I'm gonna allocate the node within that node pool. So the cool thing about C is that I can increment the counter and instantly get the pointer to the allocated node, right? So I can write an allocator with a single line. This is a single line allocator. Can your standard C library do that? Can you implement an allocator with a single line? That's pretty cool. Easy peasy lemon squeezy. All right, so here we allocated the node, and let me think. So we probably want to have some sort of a function, right, which inserts the text into the tree, right? So you want to have something like insert text, and here we're gonna accept the root, and here we're gonna accept the text that you are about to insert into the root, and this entire thing is gonna just recursively do that stuff for you. And is just gonna do recursively all of that for you. Okay, but here is an interesting thing. If you're trying to insert an empty text, right? If we're trying to insert an empty text, what should happen? If text is, like if we dereference this thing and you realize that this string is empty, what should we do? Well, you're trying to insert an empty string into the tree. Well, we shouldn't do anything. So this is sort of like a base of the recursion, right? Pretty straightforward, nothing much to say. Otherwise, if it is not empty, there's something in there, we wanna take that character, right? We wanna just take that character and basically find a corresponding child in the root, right? So we're gonna do something like root children, and we're gonna find it in there. So, but it could be missing, right? It could be missing. So we need to check, right? We need to check that this thing, if it's equal to null, the first thing we want to do essentially is allocate a new node, right? So we're going to do alloc node, and there we go. So here's the new node. Here's the new node, and after that we might try to insert the text into that node. So we take this as the new root, and we are inserting the text that is one character shorter, right? So we're inserting the text that is one character shorter, which is basically text plus one. And I think that is it. Am I missing anything? Like, is it that simple? I think it is that simple. Okay, so... Oh, all right. One of the things I probably want to do, we want to assert, right? We want to assert that root is not equal to null, right? So it's always expected to have something, right? That's pretty cool. We can also assert that text has something, right? It's never equal to null. Things are always equal to things. Though for the text specifically, we can do something like text not equal, maybe equal null, or it's empty. Then we do return. Okay, so here we can insert the text. So I guess we have to allocate the root first, right? So let's create the root and let's allocate the node specifically for the root. Interestingly enough, so we kind of assuming that alloc will zero initialize the allocated node, which is currently true because the pool is located in a static memory, and as far as I know, the static memory, like the global things, are in a BSS section, so they are initialized with 0 for free, right? So we don't have to do anything, but just in case we can do something like this, because I don't know, I don't trust it. I do not trust it. So that means since we never free the nodes, we don't have a way to free the allocated nodes. Every node we allocate is a fresh one, not the reused one, so we never have to explicitly mem set it to 0. So this invariant is always true, right? So okay, we don't have to do anything apparently. I don't think so, at least. Okay, so can we now insert the text? Let's do insert text. I'm gonna do a root, right? And I'm gonna try to insert the text hello, right? So here is a hello thingy. So, and here is an interesting thing. We can have like array of roots, right? So we want to have array of roots for different starts, but we can have like a single root. So because a single node is already array of nodes, right? It's already array of nodes, so we can reuse it as the array of nodes, right? So we just allocate a single thing, and that's basically like a first layer of roots, and that should work, I think. Okay, so let's actually try to recompile the entire thing. No target specified. Oh shit. Okay, so here in Emacs there is a pretty cool command make, right? Which basically runs make, but it's hard coded to use the make subcommand, right? So given the you have to set it to something like else, right? You have to do make prog. So let's say it's set make prog build.sh, right? And then I'm going to try to build it. And here is a cool thing. I can have a window, all right, with all of the variants in here, which is super convenient. Okay, so we have a known type node, and this is because I declared that type slightly incorrectly, right? So let's actually do something like this. Right, so this is going to be node, and then I can do it like that, and then I can rebuild the entire thing. Okay, so it doesn't have assert. Let's do something like this. assert, and I'm gonna do it like this. So all right, this stuff. I can see what's going on. All right, so let's do it like that. Array subscription as a okay, so here we start to have a little bit of a problem, right? We have to explicitly cast the character to size t, I suppose, right? So let's actually allocate something like index, right? At least define. But I mean, technically I'm allocating the local variable on the stack, so I'm technically correct, right? So I am in fact technically correct. So let's do it like that. Okay, so where is another text? Here it is. Alright, so, and I think we are in fact done. There we go. So Vim apparently out of the box also has something similar to compilation mode of Emacs, and it's actually pretty cool. So, so essentially you just do a make command, right? And it just calls whatever thing you put into make prg, right? So make prg is the command that will be called by make, right? And if after the make you have any errors, right? If after the makes you have any errors, I probably have to do it like that. So let's do it like this. You can always do copen, which opens a window with all of the errors, and you can actually click on them and jump there, right? And what's interesting is that you can fix the error and rerun the make, and the window will still stay, right? So you can kind of have like a similar workflow as with Emacs compilation mode, right? It's actually a very obscure feature. Nobody really talking about it in Vim, and this is one of the reasons why I like stick with Emacs, because I thought Vim just couldn't do that, right? But apparently Vim users don't like to talk about it. Or maybe the Vim users don't really know about this feature, because this is a very useful feature, right? It's just like Vim has a lot of like hidden things that even like professional Vimers like don't know about. It's just like there, just like Emacs actually. What study tips would you give to someone starting a career? You're so young and do so much. I'm actually not young, I'm 30, first of all. Second of all, I don't usually do career advices because I'm a Twitch streamer. Dude, listen, do you really want a career advice from a person who's, you know, earning money by being a clown on the internet? Do you really want a career advice from such a person? Just think about it twice. Seriously, you don't want a career advice from me, trust me. So... I don't know, just do what you like, right? Do what you enjoy, but that's a very generic response, right? So, I don't know, but that's precisely what I do. I just like do what I enjoy, and that's it. Anyways. Okay, so how can we test that this shit works? Is there any way except the debugger? Let's actually see. Tree, so at least it didn't crash, right? So at least it didn't exit with non-zero exit code, so which is kind of cool. We can try to do this thing where we GDB, then we break on main, then run this entire shit, and there we go. So we allocated a root. Here's the root, so it's completely initialized with 0. We have 256 zeros. Then we insert the text, and if we take a look at the root yet again, right, as you can see, 104 times it's 0. Then we have this thing, and then it's 151 times 0. So basically it's allocated like a single node in here. And we can try to take a look at it. So if we just take children 69, right, it's going to be 0. And if we take a look at the children h, it actually exists, right? It actually exists. Then we can go a little bit further and take a look at Z, right? And it doesn't exist, but E does exist. So as you can see, you can go through this through these nodes, spelling out the word hello, right? So that's what we can do in here. And as you can see, we get further and further into the node pool, right? So this is basically an offset within node pool. So it's going to be children, and here is the hello. And if you take a look at that specific node, it's completely zero, so there is no any other children in here. So we went the whole path for hello. We spelled out hello. It's pretty cool, I guess. We can try to write a simple like printer, like a tree printer or something. Or we can actually dump the graph viz. Right, we can try to dump the graph viz. The question is, what can we use as the ID for the node? I suppose nodes have... Oh yeah, we can just use the pointer as the ID of the node. Or maybe an index within the node pool array. And it's actually super easy to compute the index within the node pool array by knowing the pointer, because you take the pointer to your current node, you subtract the node pool, and you get the index. So that's how easy it is. And then you can use that index to, you know, have an ID for the node in graph viz output, and then you can just have something. Let's actually visualize this tree. I think it's going to be very interesting. I think it's going to be very, very interesting. How do you take the end of a word when one word is a prefix of another, like so and sodding? I don't. Okay, so let's open tree. So dump dot, right? We're gonna accept node root, and how are we going to do this kind of stuff? How are we going to do this kind of stuff? This is actually very interesting. So let's actually call it not dump dot, but dump edges. No, we're not only dumping edges, we're also gonna dump the nodes themselves, right? So the first thing we'll have to do for this thing is just dump the definition of that node, right? And then all of the edges to its children. So yeah, I think it's actually dump dot. Right. So how can we find the index? As I said, you can take the pointer to the root and subtract node pool. And that way, in fact, you get an index within... Well, do you get an index within that array? I think you also have to divide this thing by the size, right? Oh, no. Since it's a pointer to the specific type, the pointer arithmetic in C will actually give you the value in elements of the arrays, not absolute. I've been programming in Porth for too long. In Porth, there is no like C-like pointer arithmetic where the pointers to specific types actually step by the size of that type, because there's no proper types in Porth. So all of the pointers, they act like void stars, right? So, and you have to constantly think about the sizes of the elements and stuff like that, which is actually kind of not that bad. It's actually kind of not that bad. So the fact that in C, sometimes you have to think in terms of elements and sometimes you have to think in terms of bytes creates a lot of confusion and a lot of room for the mistake. What's interesting is that if you program in a language that always forces you to one thing, always think in terms of bytes or always thinks in terms of items, like in case of a Porth, always think in terms of bytes, you have less room for an error because it's consistent, right? So, and your brain sort of adapt to always think in terms of bytes, and at least my brain, so it's primarily an anecdotal case, but it's just like something interesting that I observed by myself, that in Porth I just make less mistakes because like you don't have to think in terms of two different things, like items and bytes. You always have to think in terms of bytes, and you just accommodate for that. And yeah, that's it. All right. So, I think I just got why I was faulting earlier today. You confused bytes with items, right? Right. It's a freaking classic. It's a freaking classic. Anyway, so this is going to be something like this. So here's an index, and that gives us the index within the node pool array. So I don't remember how you do graph viz shit. So it's going to be graph viz example. I want to take a look at the example. So show me a very simple. I don't need a sophisticated example. Can you just show me like a very simple one? Thank you very much. Just don't. And it also takes a half of an hour to open a simple example, because why not? It's 2021. Graph with simple example. Maybe I have to like dot simple example. Yes. Show me a very simple. That's what I wanted. Really, that's literally what I wanted. Like, I didn't need a gallery with all of the possible fancy shit. It's just like literally give me that, because I don't remember the specifics of syntax. Anyways, so what we can do here is just declare that we're gonna have a node, right? 1, 2, 3, 4 node, and then we're gonna use the index to define this thing. So this is gonna be index. All right, so we're also gonna, do we have to put semicolon? I don't think so, right? So no semicolon is required. So, and after that, I just need to connect that root with its children. So we'll have to iterate the children. So let's do it like that. So how many of them? I can do something like this. I can do size of root children, and that gives me the amount of children. Though it gives me the size in bytes, I need the size in items. Yes, of course. Thank you, C. Very cool. So I will have to do something like size divided by size of root children 0. So usually what C developers do, they come up with the following macro, something like array length. Right, where, oh, the fuck is Emacs? What the fuck are you doing, Emacs? Okay, so you have to do something like size of access divided by size of access 0, but maybe it would make sense to actually, wrap it in parentheses, and then we're gonna wrap this stuff like this. Ooh. Excuse me. COVID, by the way. Size of isn't a function. See if I care. Anyway, so where is the size of? Here it is. Okay, so it's gonna be array len root children. There we go. So it's an operator. Yeah, it is actually an operator, which is kind of interesting. And I think you can use size of similarly as you can use return, right? So you can do shit like size of int, and it is correct if I'm not mistaken. It's just like nobody does that. We can actually test that. This is actually, I feel like you can do that. It's kind of interesting. I remember something like that. Okay, let's actually try to compile this entire thing. No source file starting. Okay, so C open. Oh, okay, so this is because I have to do PRG build. I probably have to put that into my, thingy. So expected. Okay, you can't do that, which is kind of weird, right? So why there's such inconsistency between these sort of operators like return and size of? Right. So. I don't know. So I think because of that, Casey quite often returns with parentheses, right? So to be consistent between size of and return, I think. Maybe that's his justification, but I don't know for sure. Right, so... it only works for the variables. Let's actually see. It's actually very interesting. Oh, it does work for the variable, doesn't it? No, it's kind of hard to tell. It actually does work. Would you look at that? So we can try to run this entire thing and use tree, and it returns 4, and it is in fact 4. Integer is 4 bytes. Would you look at that? So that's kind of cool. So it doesn't work with types apparently, but it works with variables. So yeah. So it's like nobody uses it this way. Nobody uses it this way. And again, that's probably why Casey wraps return in parentheses, just to stay syntactically consistent with size of or something like that. But I don't really know his like exact justification. And in fact, at the end of the day, it doesn't really matter because it's all that is just calls of the bike shed. Ryukisa said it's his habit from the old days when C couldn't return otherwise. Oh, okay, that actually makes sense. All right. Okay, so doesn't really matter. It's just like, yeah, colors of the bike shed. In fact, I don't really care about specific coding style. It's just like every time I join other project, right, where there is established coding style, I just like basically adapt to that coding style, and yeah, I never like care. Like I never choose a project because of its coding style. It would be stupid actually, but yeah. Anyway. So let's continue. We need to iterate through all the children, and we only care about the children that are not null, right? So we want to do something like children I, and it's not equal to null, right? So if it's not equal to null, what we want to do, we want to actually have a child index, right? So we want to have a child index. So let's define child index. Root children children I minus node pool, and that gives us the child index, which means I can do something like printf node zu to node zu. And it's going to be a new line here. I'm going to provide the index, and here we're going to provide the child index. And that is basically it. After we printed that edge, we're going to actually go recursively down and just do root children I. So that should be enough, I think. That should be enough. And we can insert text hello, then we can try to insert other texts like helium, right, just to see how it will go. So basically the example that we did at the beginning of the stream. And let's try to dump the dot files, right? So it's not going to be a proper dot file, so I just want to see the edges. You know what, let me actually go to my vim rc, and I'm going to simply set make program build sh. Because again, thank you so much for Twitch Prime subscription. Thank you, and welcome to our epic Prefix Tree Club. That's right, we're implementing Prefix Trees today, and that means we're epic Prefix Tree Club. Okay, so if I open this thing now, tree, and I do make, it uses build sh. Okay, so it's hard coded like this. All right, so now I can try to run the tree, and here are the nodes, right? So, but they're not wrapped into a body, right? So one of the things we want to do probably, we want to wrap all of that into a body. So it's going to be printf. So I think it's a dgraph tree. Then we dump the nodes, and then we do print something like this, and that should be fine, right? And tree, there we go. Here's our tree, which we can try to render, right? Let's try to render that tree. So I have an idea. We can do this thing, then we can call it and just dump the output to tree dot, right? So as you can see, yeah, there we go. So we have a tree dot. If you take a look at this thing, it's a tree dot. After that, I can do dot tsvg tree dot, and we can redirect that to tree svg. And that should be enough, in fact. So let's take a look, and then I can open tree svg. There we go. So here is the tree based on two words, hello and helium. Right, so first 4 characters are like the same. It's actually, yeah, this one, the first one is not a character actually, right? It is not a character. So the characters are more like edges, right? They're more like edges. And maybe this is something that we have to emphasize in here, right? So we have to emphasize that the edges are the characters, not the nodes. So, and by the way, this is one of the ways we can indicate the end of the word, right? So we can always, this is not what I wanted to open. We can always add something like a Boolean flag in here, right? So if we reach the end, this is where one of the words end, right? If you, for example, we have hello, helium, and hell. Hell is basically a substring of hello, and by marking it as the end, we can indicate that, yeah, there is such word in the set, in the tree itself, but we don't really need that right now. Maybe we will need that when we implement like a simple auto-completion, right? But for now, I don't want to bother with this kind of stuff. So let's actually put some labels on the edges, right? Let's put some labels, and labels, you put them, I think you put them like right here, right? So there's a special thing in here, label attribute. Yeah, there we go. So you can put a label on a node, but you can also put a label on the edge, as far as I know. So let's see. So, and the label is, label is going to be C, and let me just put it like this. It's I, and I think it's, yeah, we can just use I, right, whatever. Might as well just cast it to character just in case, because who knows. Right, so it's gonna be built, and if I now refresh this entire thing, there we go. So we have things like hello, right, and for the hello it goes here, but for the helium it goes down there, right? So, which is pretty convenient. So it's pretty cool. Spread is pretty cool. We want to have like more stuff, right? I actually want to build a way bigger tree. That means I need more data. Where can I get more data? Lazy Grid, thank you so much for 5 months. Sojin cool indeed. Thank you so much. Thank you so much for 5 months of tier 1 subscription. Thank you, and welcome to our epic tree club. Or is it try? Is it tree? I have no idea. Okay, so I have a very cool thing in one of my projects, actually. So I have a project called Gym. If you never heard about this project, I really recommend to check it out. It's basically immediate mode JSON serialization, but it's not the point of today's stream, right? It basically allows you to create JSON by doing this kind of stuff, like similar to immediate GUI, but it's an immediate JSON serialization. I'm gonna put this thing in the description for anyone who's interested, of course. So Gym. So let me actually give a more precise description. Immediate mode JSON serialization library. And so can I copy paste this thing in here? Okay, so there we go. So here's that. And in examples, it has a very interesting file, right? It has a file called fruits, right? So fruits.h. So let's actually open this file. This is just a list of fruits, believe it or not. So if you look at it, it's a huge array. It's not that huge. It's a big array of fruits. And I usually use this array to test things like that, right? So, right, just to have some random data to put somewhere. And I think I'm gonna just yoink this file and put it into my project and just basically build a tree out of all of these fruits. Sounds good? Sounds good? Sounds too good? Let's fucking do that. I think it's a pretty cool idea. So I'm gonna download this thing, yoink. Alright, so and now I'm gonna go to tree.c and I'm gonna include the fruits. Fruits.h, right? So if I separate, I open the fruits. So we have fruits themselves, so here is the array, but on top of that we also have the size of the fruits. So the thing we can do now, we can remove all of that shit, we can iterate through all of the fruits. So it's gonna be size t less fruits count plus I, and then I insert the text into the root and I do fruits I. There we go. So we inserted shit ton of fruits in here. So let's go ahead and just build this entire thing, and we fucked up on the line 99. Let's go to tree dot and let's take a look at the line 99. Cool. This is because we have a space. Do we really want to have a space in there, right? So what we're gonna do with the space, we're gonna allow the spaces. Though, if I wrap it in like quotes, right? If I wrap it in the quotes, is it gonna work? Right. I keep forgetting that it's not main, it's actually tree. So dump dot. So let's give it a try. So what if I say something like this? Is it going to work? Didn't work. So now we have a syntax error at line 3 near this thing. So it actually failed harder than before, right? It straight up failed at this thing. I really like how it looks like apple Oh, that's actually very cool. I really like that. Okay, so the tree itself should actually probably look insane. I'm really looking forward to it. So maybe instead of like single quotes, you have to use double quotes. Maybe that's the only thing that that GraphViz support, right? So dump dot, and let's actually do it like that. But then I have to escape this entire stuff, right? So it is what it is, and it isn't what it isn't. Let's make this, and it worked. Perfect. So are you ready, chat, to take a look at epic tree build of all of the possible fruits? So here is the holy fucking shit. That's a lot of fruits. Holy fuck. So that's the tree we're building here. I really don't like how obscure these nodes are. You know, it would be nice if the nodes themselves like had the character. But it looks so fucking cool. Yeah, so here is the prefix tree for all of these things. And you can use this tree for auto-completion, right? You can start typing like first few letters, like you can start typing K, and it narrows down all of the possible auto-completions to just this subtree, so you can quite easily ignore like literally everything, right? And you can, like, you pressed K, and you already know what kind of like subset of words you need to autocomplete. That's actually very cool. Really like that. Even though we use 200 kilobytes per character, like each node right now is 200 kilobytes. But again, it's 2021. Just buy more RAM. Come on. Or download it from the internet. I don't know. So many fruits. I really, like, I don't know why this thing bothers me so much. I wanna replace the nodes with the characters, with the corresponding characters. But to be able to do that, I'll need to, goddamn. So that means I have to put the definition of the node not at the beginning of this function, but actually before. So I have to, the parent has to define the children. That's how it has to go. So then we have an opportunity to set up the label. Okay, that's fine. I would say that's fine. So here that means for the label, I'll have to do something like label. It's gonna be C, and then here. So this one has to be the child index, and here we're gonna have the char I. So that should produce a better result, probably. So now instead of node number, we would have like actual characters. There we go. So here it looks a little bit better now, I think. So the root looks like this. So here is the root. But we can actually set the root to something, you know, something, and you know, the usual thing. So printf node 0, and we can set the label to, I don't know, root. Let's call it root. So this one is gonna be, though, like, we never know that the root is 0 actually, right? So it would be better to actually do something like this. And then we can do root minus node pool. And this one is going to be something like this, right? So this can be a build. Yeah, there we go. So here's the root, and here's the rest of the characters in here. And if you take a look at this kind of stuff, so here is the prefix tree. God damn! This is something worth committing already. What do you guys think? I think I'm gonna commit this shit and actually upload it to GitLab for everyone to play. So that's already something interesting. I really like that. Pushy, a committee. That's right. I actually want to rename prefix tree to tree. I really like this name because it's so short and sweet. So license. Goddamn, I don't have a very convenient, you know, shortcut for MIT license. So maybe I can copy paste some stuff like from Porth. I'm gonna take the license from Porth. There we go. So it's easy. Modern problems require modern solutions, though we don't have any Porth contributors in here, so I'm gonna actually remove them. So what about the readme, right? Readme. So prefix tree, implementation in C, right? So references, and in the references I'm gonna put the thing I found on Wikipedia, right? So this is gonna be the description. HTTPS. There we go. Is that it? Reference. Whoa. So okay. So we're also gonna have something like a quick start, right? Quick start. And here we're gonna have something like console build sh, and then you wanna, I don't know, open SVG. What's the most common SVG viewer, right? Chat. When you wanna view SVG file, what do you usually open it with? What do you usually open it with? Do you always open it with the browser? XDG open. Okay, so XDG open is actually a pretty good idea. XDG open, right. So for those who doesn't know, XDG open is basically tries to identify the type of the file, right, by its, you know, maybe extension. I don't know if it looks into the contents of the file. I think it associates only with extensions and tries to open it with the corresponding program, like similar to how Windows Explorer works, right? On Windows, you can associate the file extension with a specific program, and when you double click on that file, it will open with that program. So it's kind of similar system, but for Linux, right? So XDG open kind of makes sense to use in here, right? So, and I'm going to do something like tree SVG, right? And whatever you have in your system, right, you can open it with that. So, all right, so we have that. Do we need to have anything else? Maybe we need to have git ignore, right? We need to git ignore dot file and SVG file, and also the executable itself, right? So let's go to git ignore. So this is going to be dot file, then SVG file and executable itself. There we go. So let's do finally git init. Let's take a look at status, and that's the only files we want to add, and we're going to add them. Right, so let me take a look one more time. Did we add everything? We didn't add git ignore, and let's commit. Ready, set, go, boom. And we don't have anywhere to push. We have to create that repo first. New project. Let's create a new project. Create blank project. Okay. So my awesome project. No, it's my awesome project. Let's call it tree. And what's going to be the description? Let me take a look. So here. It's not readme. The fuck? Prefix. Maybe. Right. So. By the way, I recently learned that you can quite easily copy into the X buffer in Vim, and that buffer is like plus or star. And yeah, it's actually kind of cool that you can just select a thing and just have that in the X buffer. So that's pretty cool. Okay. So this is gonna be public. And I set initial. Oh, god fucking damn it. It initialized it with this crap. I forgot to uncheck the... God fucking damn it. So... I hate when the software tries to be smart and helpful. It never is. So I think one of the things we can do, we can force push that shit, right? So if I do remote add origin, right? Remote add origin. And if I try to push now, right? It will not be able to push because there are already some commits there. It actually pushed. I'm confused. How did it push it? Because I would presume... I know why. Because GitLab by default created main. I'm sorry. Okay. So can we... First of all, maybe I can remove the remote master. Let's start with removing the remote master. I'm going to do push origin and master. So if you want to remove the remote branch, right? You basically push that branch with the colon in front of its name, right? So we're going to do that. So that's the first thing we want to do. So we removed the remote master, but the local master is still there. So the next thing I want to do, I want to rename my branch. I have no idea. I don't remember how you rename the branches. So we want to do something like git branch help. And let me see, rename. How do you rename? To move a branch and the corresponding move rename branch. Okay, so maybe this is how you do that. Branch M, and you do master and rename it to main. Right, if I take a look at the branches, I do have main. If I try to push the main into the origin now, it should fail because we have a commit generously generated by GitLab, right? So it won't work, right? It should not work. That's precisely what I was expecting. But if we force push it, it will work now. Okay, remote rejected. So you are not allowed to force push code to protected branch. Okay. I'm just thinking at this point, what is easier? Going to the settings, figuring out how to unprotect the branch and then force push to the branch and protect it again, or delete the entire thing and create again. What is easier at this point? If you think about it, right? What is easier? I feel like removing the entire shit is just easier. So yeah, I'm gonna go ahead and remove it. So where is the, I think it's an advanced, right? So, and yeah, delete the project, there we go. So it's gonna be sodding tree. Yes, delete the project. Okay, let's new project. Okay, don't forget to fucking click that shit. Tree, alright. What a journey. What a fucking journey. Holy shit. Welcome to a modern software in 2021. So this is a public, alright, so let's create a project. Cool. So this thing is effectively, why does it still have this shit? Did I forget to unclick and, fuck's sake, it had, like, I thought the second checkbox is not gonna create, okay. Oh, and I also created it in the wrong. Okay. So let's go. New project. Blank project. Enable static application security testing. Analyze your source code for security vulnerabilities. But nowhere in here it says that it will make an implicit commit. Like, how on earth does it... Okay, so let's actually do it like that. Hopefully now it's going to work, right? Like, why they never mentioned the most important part of these things is that it creates an implicit commit, so you can't force push or anything like that. Like, why is that a thing? I don't understand. Finally! Holy freaking shit, that was so hard. Okay. Let's do add origin and remote add origin, right? Remote add origin. And is that the correct thing? Okay, so git push origin main. Finally, we did it! Holy shit! That was hard. But we fucking did it. Is it private? For fuck's sake, it's private. Okay, so let's actually go on private. Okay. Visibility. Like, at least this one is actually pretty straightforward and easy to do. Right, do we have to click something like apply? Yeah, save the changes. All right. Okay. So you can find the source code of this entire thing in here, and I'm going to put it in the description as well. There we go. Right. Tree source code. Right. There we go. Here is the source code we've developed so far. Okay, so this is not that. Wait, did I actually say make? No, I actually said build sh. Okay, so everything's fine, and then I can open the tree SVG, and here's our prefix tree. That's pretty cool. You know what? What's gonna be the next thing that I'm gonna implement? I want to implement a tool that basically accepts the prefix, and then it uses this tree to suggest autocompletion, right? So maybe you can put A in there and it will suggest automatically apple, apricot, avocado, right? So if you type A, as you can see, we have 3 options in here, and it will basically do a DFS and just suggest all the options. And this is, by the way, where we probably want to know the ends of the words, right? And this is probably where we're going to introduce the Boolean flag that indicates the end of the word. Right, so that's actually pretty cool. Let's go ahead and implement that. So, but maybe before we go ahead and do that, I want to make a small break because I need to refill my water, right? It's kind of difficult for me to continue working without the water. So, so let's go ahead and implement like a, sub command that accepts a prefix and then suggests autocompletions. But maybe we want to separate different functionalities into separate sub commands, right? Because I don't want to remove the functionality of dumping the tree into graph.res file, because I think it's actually kind of cool. So let's go ahead and implement subcommands, right? Okay. So let's accept the arguments, right? Let's accept the arguments. So the first thing we want to check if you have enough arguments. You have to basically supply at least one argument, which is the subcommand, right? If the amount of arguments is less than 2, we're going to say something like usage, right? We're going to have a separate function that prints the usage, right, in a centralized place. Usage, and so we're going to have a control over where you can print that thing. You can print it to std out or std error. So because of that, we're going to customize the sink into which you can basically sync your usage. Let's literally call it sync. I think it's a pretty good idea. Why not? And in here, I'm going to print something like usage, right? So this one is going to be tree. And then you can supply the subcommand, right? So this is going to be a subcommand. And in terms of subcommands, we're going to have like 2 of them. So the first subcommand is going to be, let me think, right? The one that prints the dot file, right? Subcommands. So printf sync 1, 2, 3, 4. So let's call it something like dot, right? I think it's a pretty good subcommand, right? So, and the second subcommand will basically accept the substring or prefix and then generate auto-completions. So how should we call such subcommand? Let's actually call it complete, right? It's going to accept the prefix, something like this. Sounds pretty good. So let me think. We need to basically provide this short description of each of the subcommands. So for the dot, we're going to do dump the tree into a graph viz dot file, right? Suggest prefix auto completion based on the tree, right? Based on the tree. I'm not sure if it's a good description. Suggest prefix auto completion based on the tree. I think it's a good description. I think it's more or less clear. Right. So, and again, if you didn't provide any subcommands, we're going to print the usage into the standard error, and we're going to say something like standard error. So let me replace this thing. Error, no subcommand is provided. Right, and then we're going to exit with non-zero exit code. There we go. So the next thing we're going to have, we're going to grab argv1, and basically assign this entire thing to the subcommand, right? So this is going to be subcommand. And in here, we're going to have like a switch case for, well, there's no switch cases for strings in C, but we're going to have if else that dispatches to each individual subcommands, right? So if subcommand is, well, you have to compare things like this, strcmp, right? So we want to do dot, right? If it's equal to 0, we're going to do this thing where we build the tree out of fruits and then print the graph viz file, right? So that's what we want to have in here. So then else if strcmp subcommand complete, and this is something that we'll have to implement, right? I'm going to put assert in here saying that this thing is not implemented yet. Complete subcommand is not implemented yet, right? So, and otherwise we found an unknown subcommand, right? We're going to do something like fprintf. Maybe first we want to print the usage to let the user know what subcommands are available, right? So we first print all of the options and then we say, well, you picked the wrong options. Here are the options, right? So usage std error, right? Std error. Error unknown subcommand, and we're gonna do something like s and then we're gonna just put the subcommand in here, and then I'm gonna exit with non-zero exit code, and that should be it basically, right? So we implemented a simple subcommand subsystem. All right, so let's try to build the entire thing, and something is wrong in here. Let's take a look at this stuff. So exit does not exist, so we have to include the standard library, stdlib. Right, so strcmp, so that means we have to include the string. Right, we have to include the string, and I think that's it. As you can see, it even, oh yeah, it even failed because we call tree in the build. Right, that's actually pretty cool, right? So we call tree in the build. So it means we have to go to the build sh and actually call it with dot, right? And if I try to do this thing, it actually works correctly. That's actually perfect. So now you can just print the graph.viz file, or you can try to autocomplete things. Right, but right now it's not implemented yet, so this is something that we want to do. Okay, so maybe I'm going to commit this entire stuff. So let me take a look at the status. Git add build.sh tree.c git commit. All right, so what we want to say in here, implement simple subcommands system. Right, I'm going to push origin main. There we go. So the latest changes are in the repo. Cheers, by the way. Okay. I keep typing main.c instead of tree.c. Okay, so when we want to autocomplete something, right, so we need to get the prefix, right? So here what we need to do is, well, this is not particularly convenient, I think, right? This way of handling things where I directly index argv is very inconvenient because it does not allow me to consume the arguments quite easily. Right, you know what? Recently I started to basically handle the arguments the following way. Right, so first thing I do, I grab the program name, right? Program, argv, and then I think I can do ++. Oh shit, that's actually very convenient. Right, so this thing, I don't quite remember, like if I try to do something like this, will that thing work correctly? Right, so who has higher priority? I think ++ has a higher priority, so it will take argv, increment it, but return the previous one, and we're gonna dereference the previous one, so that's very interesting. Okay, so basically I shift this thing by just doing that. Right. So, and then after that I can simply check if this thing is null, right? If this thing is null, no subcommand was provided, and I can accept the subcommand like this, right? That's actually very cool. So ++ is the highest, yeah, it does make sense, right? So ++ increments argv, but the whole ++ thing returns the previous one. We dereference the previous one and we use it for our things. So that way, it's actually way more convenient to handle things. So let's take a look. So it's going to be build, unused variable. We can try to use the program variable. The way we can try to use it is basically make usage accept the program name, right? So this is going to be const program, right, and then just use it in here, right, because the program, right, the first argument in the argv depends on how you call the program, right? It contains the path with which you call the program, and if it has some sort of an alias, like a symling or hardling, it's going to be reflected in the program name. So we can use that name in the usage as well, right? So to be more accurate. Right. So, and this is where we're gonna accept the program. So where's the next usage? So this is another program, and I guess that's it. So if I try to do this thing, it seems to be working, it seems to be working, right? And if I run this thing, okay, it wants a subcommand, I provide dot, I provide a complete. Yeah, I think it's like, this is a very convenient way of handling the arguments, of parsing the arguments, because you sort of like treat it as a tokenizer, right? argv turns into a tokenizer, right? You want to consume a token at a particular point, you just say, give me the token, right? And you just keep consuming them, and then also, you know, branch out depending on the tokens that you encountered and, you know, parse things differently. Okay, so if we went into the complete sub-branch, right? First thing we want to check if the user provided the prefix, right? We can check that by doing something like this, argv. If argv is equal to null, we have to say that we expect the prefix, right? fprintf. So also we want to do usage, stderr program, right, like this. And here we're gonna do error, prefix is not provided for the, prefix is not provided. Maybe no prefix is provided. I think it's over there, and then we exit with the non-zero exit code. Okay, so we have everything. We have the subcommand, we have the prefix. We probably want to save the prefix like this. Prefix argv. I'm going to reference this thing, and there we go. So we have a prefix. So how can we use that prefix to generate all of the possible autocompletions? So I suppose we need to use that prefix to find the subtree, right? So there we go. So we have prefix as a, right? We need to find this subtree, and then we need to grab this subtree and DFS it and basically print out all of the possible paths in that tree. So we need some sort of a function that, given the prefix and the root, can give us the subtree defined by that prefix in that tree. Right. So let's try to do that. So we're gonna have a function, let's call it find prefix. I'm not sure if that's a good name, but I cannot come up with anything better. So it will return the subtree, but it will accept the root and the prefix, right? It will accept the root and the prefix. So how is it going to work? Well, if the prefix is empty, maybe we can do in something like this, prefix equal to null, or it's empty, we can instantly return the root as the as the subtree that contains that prefix. So this is basically the base of the recursion. Then if it's not empty, we need to assert that the root is not null, right? And then we need to take the children, right, and then use that prefix. So here is this thing, but here is an interesting thing. What if the children is empty, is null? I think in that case we just have to return null, indicating that we couldn't find such prefix, right? So, but here is an interesting stuff. If we allow the root to be null, we can actually quite easily do something like, if root is null, just return null. And then we can continue recursion, and that situation handles itself automatically, I think. Right, and then we can just do something like this. Right, I guess that's it. So if we try to find the empty prefix, we already found it, that's the whole root. If the root turned out to be null, there's nothing to return, we just return null. Otherwise, we just find the corresponding child and we chop off a single character and continue the recursion. So if the child turns out to be null, this condition will handle it automatically, so we don't have to worry about this kind of stuff. What's interesting is that all of the recursions in both find prefix and insert text, all of these recursions are iterative, so maybe we will be able to replace them with while loops, right? Because they basically they linearly drill into the tree, right? They linearly drill into the tree. So let me see. Okay, let's actually compile this entire thing, and prefix. Okay, so it wants to do something like this, and unused variable prefix. Okay, that's fair enough. So it complains about this thing. Oh yeah, okay, so I have to explicitly cast it to something like size t, otherwise it's not subscriptable. So, and then let's make it one more time. So it complains about the prefix not being used, and that's fine. So let's actually find the subtree. So subtree, find prefix, we provide the root, right? We provide the root and we provide the prefix. And here is the subtree that contains all of the possible suggestions. So to be fair, we need the tree for both of the subcommands, for dot and for the complete. So I think I'm gonna actually extract this thing somewhere here, so it's available for all of the subcommands, right? And then I can just use that. Right, so we have a subtree, but now we need to generate all of the possible suggestions, right? So we need some sort of a function that accepts the prefix and accepts the subtree, and then just prints all of the autocompletion things. So let me see. Let's call it something like print autocompletion. Right, so this thing will probably accept the sink where you want to print all of that. Then it will accept the root from where to start printing things and stuff like that. And then we're gonna accept the prefix, right? Because it's gonna be important for printing things. Right, so this is the prefix. So there we go, and so this is how we're gonna do all of that. Print autocompletion. We're gonna print that to std out. Then we provide this subtree, and then we provide the prefix. There we go. Okay, cool. All right. That's a good question. It's a very good question. How can we print all of that? So we have a prefix. We need to keep appending things as we go deeper into the tree, if that makes any sense. So we need some sort of a buffer into which we can push the new characters and pop off the characters, if that makes any sense. Because as we go deeper into the tree, we'll need to be able to do that. So let me quickly do this thing. Maybe I'm going to call it AC buffer, right? So, and it's going to be AC buffer capacity. So, and how long of these words we want to support? Let's support 1 kilobyte, why not? Okay. So this one is going to be the character. And we also need to keep track of the size of the AC buffer, right? So initially it's going to be 0. We need a way to push a character into AC buffer and pop a character, right? AC buffer push, right? So it will accept the character that you want to push in there. And also AC buffer pop to remove the character, right? All right. So here I want to assert that AC buffer size is less than the capacity, right? So yeah, it's less the capacity, so that means we can push something there. And then I can do AC buffer size plus, and I'm gonna put ch in there. Right, okay. So, and to pop this thing, I just decrement the size, but I also want to check that the size is greater than 0, so you have anything to decrement at all, right? So because of that, I think we don't even need to provide the prefix. If the prefix is already in the buffer, right, we can just keep it there. I think that's fine, right? So I'm gonna just go ahead and remove the prefix, and we will expect the prefix to be there. So that means we'll have to copy that prefix into the buffer. But we can also make find prefix to push the characters into the buffer, so the prefix is already in the buffer. Right, that's actually a pretty cool idea. Right, that's actually a pretty cool idea. So this is going to be find prefix, and as we go, so probably need to take this entire buffer, right? So I need to take this entire buffer and just put it in here so it's available for the find prefix as well, right? So for the find prefix as well. So here is the thing. So that means I'm going to do AC buffer push prefix, right? So as we find the prefix, we push the characters into that buffer. So this thing is going to be there. So, and as we print autocompletion, if root is equal to null, that means we reached the end of the tree, right? We're going to just print whatever we have in the autocompletion buffer, right? We can just print whatever we have. To do that, we can use fwrite command, right? So which accepts the pointer, AC buffer. All right, then the size of a single element. So we're gonna use the size of the buffer, and we're gonna say that we have one buffer, and then we print that all of that into sync. It doesn't print the new line, so we can use something like fputs, maybe fput C for the new line, right? So there we go. It's gonna be something like this. It's gonna be sync, and that's it. Okay. So now, as we go further, what we need to do, we need to iterate through all of the children of the current node, right? We need to iterate through all of the children. So we're going to do the following thing. So it's going to be size t, array length, root children, right? Plus I. If root children I not equal to null, right? What we need to do is push that character into the buffer. So this is going to be something like char I, then call print autocompletion recursively on that child, children I, and then pop that character. There we go. So that should be it, actually. I think that is basically it. Right. So we're using the buffer to keep track of all of that, and it's fine. Right. Okay, let's try to compile that and see if we made any mistakes. Okay, so you open, anything else? So we don't have to provide the prefix anymore, right? Prefix is not needed, and it seems to be working. Okay, so that should work. That should work. So let's go ahead and see if it actually works. So we have to provide complete. What if I provide A and it didn't work? That is so cool. Holy fucking shit. If I don't provide anything, if I provide an empty string, right, theoretically it should basically print all of the suggestions with an empty string, but it didn't print anything at all, which is kind of worrying. So let me see what's going on in here. So tree.c. Autocomplete. So print autocompletion. So print that in here. So we can actually try to debug this entire thing. Let's actually go into the debugger. I think it's gonna be way better. So let's break on main and let's run with complete A, right? Okay, so we're going to initialize everything. Goddamn it! Let's break on 128 and continue. And the subcommand that we've got is the autocompletion subcommand. Okay, that's cool. So here's the prefix. If I take a look at the prefix, here is the prefix A. Let's take a look at the subtree. Right, so here's the subtree. We do have something in the subtree, so there's like different things in there. And let's take a look. Let's step into this thing and all right. I think I forgot something very important. I think if root became null, you have to print the suggestion and you have to return from it. This is one of the things I forgot, but I'm not sure if it's going to fix anything, right? So that's kind of the problem in here. So let's actually go and try to quickly fix that. So print autocompletion. So after that, like I would expect this to just return, right? Because it's like a base condition. And let me try. So if I try to complete A, it still didn't do anything. So that was not the case. All right. So if we find this thing, so let's break here and continue. So we found something in here. So here's I. And 112, right, 102, 12 actually. Oh, right, so it's J, it's octal, but we need decimal. So this is actually P. Okay, so that's fine. So when we continue doing this thing. So what if I break on 94 and just continue? Can I unbreak this thing? Delete? No breakpoint number. Oh, okay. So breaking and breaking is just like not so inconsistent. It's just like infuriating. Okay, so here is an interesting thing. So it feels like this condition that we've gotten here, right, is never going to be executed because we never reach it, right? We basically never reach it. So maybe, yeah, we need an indication of the end of the word. That's what we need. Yeah, so I was thinking that we can quickly like come up with something without any of that indication, but looks like we can't do that. Because for some reason I'm too lazy to introduce that flag and go into the insert text and like supporting that flag and just like want to have something that actually works. All right, and produces something. So one of the things we can do, we can basically see if there is no children for that specific node, only then print the buffer. So that's one of the things we can do. So let's go ahead and try to do that. I think that's fine. Tree.c print autocompletion, okay. So we're gonna remove, well, I'm not gonna remove that. So let's have something like leaf true. And if you encounter any of the children, it's not a leaf anymore, so it becomes false. If you are leaf, right, we're gonna just yoink this entire stuff and put it in here. Okay. And then I want to go somewhere here and just remove this entire stuff. So it's not going to be ideal, right? So we use the lack of children as an indication of a leaf, but it's at least something. At least it's going to print some suggestions, right? So let's try to rebuild the entire thing. And of course, we have some troubles doing that. So let me take a look. So Boolean, it doesn't have Booleans, right? C doesn't have any booleans unless you include stdbool.h. That's kind of important. Never forget. Okay. So let me try. I'm gonna try to complete A. There we go. So here are auto-completions. And I can do something like complete AP, and it will suggest apple and apricot. So if I try to do like empty string, it will suggest literally everything. I can try to do T, and here is a tamarillo, tamarind, tangerine, I don't know, but that's the things. We can do S, right, so if I do SA, it just narrows it down even further, right, so cell, and yeah, here are auto-completions, so that's actually pretty cool. Right, this is not really correct way of doing things because you can have words that are literal prefixes of other words, and because of that they're not going to be auto-completed at all, right? So that's kind of a shame. We can even try to replicate that, right? So let's go ahead and just modify the fruits, right? So fruit.h, and let's find cell. So what if you literally have a word in a list of fruits cell? Because it's a literal substring of one of these options, it's never going to be suggested because it's never going to have an end. So it's going to be lost in the tree. So, and we can even try to demonstrate that. So I'm going to rebuild everything just in case, and I'm going to say tree complete cell. And as you can see, it was never suggested, right? So because it's completely lost. And the way we can fix that is by actually indicating the end of the word in the node, right? So we can have something like end, right? When you reach the end of the word, you put true there, and then you use that flag to for the auto-completion. Let's see how difficult it is to implement that. So insert text. When we are inserting text, do we always want to have the root? I think we always have the root, right? It's never a thing that we don't. That means if we encounter the end, we can quite easily say root and true. So that's one of the way we can do that. All right, so let me see if that doesn't break anything. So it's going to be make. Seems to be working. And now in auto-completion, right? In auto-completion, print autocomplete, we can use the end as an indicator that it's time to print the buffer. Right, that means we can actually do that somewhere here. So there's no need for the leaf, right? So the actual indication here is just the root and its end, right? So we reach the root and its end, we have to print the auto-completion. And that way we should see the cell in the auto-completions, hopefully, right? So let me try to do this thing. And if I try to do tree complete cell, it does suggest cell now. You see? It does suggest it. So if I do Sala, right, so it excludes them all, right? So now we keep track of the ends of the word, even when the word is literal like substring of another one. So that's pretty cool, not gonna lie. That's actually pretty cool. So let's remove cell from the fruits, because I'm pretty sure this is not a fruit. I'm pretty sure. Cell, so it's not really needed. And let's rebuild it. So I also want to update the README. So this will just give you that, and then you can do something like tree complete app, right? So that should be fine. Add. Well, what exactly did we do? So let me take a look at the div. So I think here we literally just implemented auto-completion from scratch. Yeah, there we go. Add readme tree.c commit implement autocompletion. Right, implement autocompletion. We push that right into the repo. You can find the source code of this entire thing in the description if you're watching live. If you're watching on YouTube, if you're watching live, I'm gonna copy paste the source code. Where's the source code? I think I can just grab it from GitLab. You can find it in here if you're interested, of course. All right, so I'm already streaming for 2 hours and I'm pretty much done with this data structure, right? My goal was to just take this idea that is concisely described in this picture and just implement it and see how you can implement autocompletion with it. Right, because the idea is pretty straightforward. You just take the strings and you just build the tree out of them, right? So, and it works beautifully. I really like how it works. So we managed to build like this visualization of all the fruits and stuff, and we implemented a simple autocompletion, right? So if you're planning to implement your own IDE or some sort of extension for a text editor, you can use this data structure for autocompletion. Though maybe you want to think about making it more compact, because again, we're using 2 kilobytes per character, which is kind of a waste. But again, there's a lot of ways you can improve that, right? Using smaller pointers, basically indices, like smaller indices instead of 64-bit pointers, and also smaller arrays because you don't need the whole ASCII range, right? Another interesting thing, so this works only for ASCIIs, right? So this works only for ASCIIs. How would you implement something like that for like Unicode, right? Because Unicode has like literally million Unicode points, right? Amount of Unicode code points. I think it's around million. Yeah, it's literally million, right? 1,100,000, right? How, like, you won't be able to create such a huge array, like it's even bigger waste, right? I think in that case, you would use some sort of a hash table in here, right? And it will grow as with the amount of children for specific nodes, right? So I think it will be also kind of interesting to explore this idea, but for Unicode, right? So it will require like a more sophisticated data structure. What's interesting, in the current state, this thing is extremely easy to serialize. I can just take node pool and dump it to the file system as it is, and then load it from the file system. Well, if I load it from the file system, it's not going to work because we're using absolute pointers. So next time you load it, you don't really know where in memory this thing is going to be located. But again, if we used indices, it would be easily serializable, right? So you just dump this array and that's it, it will just work, right? But you have to use the relative pointers instead of the absolute ones. So there's a lot of things that you can explore in here. So, but I explored the main idea and I'm happy with it. So it's actually a pretty cool data structure. I hope I got it right. Please let me know in the comments if I misunderstood what a prefix tree actually is. But I think I understood it correctly, right? It's like, well, what else can you, how else can you interpret this picture? Anyway, I guess that's it for today. Thanks everyone who's watching right now. I really appreciate that. Have a good one, and I see you on the next sorting session. I don't know when, I don't know where, but in any case, there will be one. Trust me, there'll always be one. So maybe we should rate somebody. We haven't rated anyone for quite some time. So, oh my god, Mr. Conti, I hope I'm pronouncing your name correctly. Thank you so much for 100 bits. Thank you, thank you, thank you. I really appreciate the support. So, is anyone streaming anything epic on the software development section of Twitch? So, let's take a look. So... Twitch is so slow, it's physically painful. Twitch interface is like embodiment of the pain. Okay, functional programming. Oh, it's not English, it's French, unfortunately. I don't speak French, I'm sorry. Rust.js. Is there anything? I didn't see anything interesting. Everything is kind of boring. Just like my stream. So there is a K Comrade streaming C++ OpenGL, but they streaming in Russian, and I don't speak Russian, so sorry. Universal Windows. I don't know. All right. Okay. I tried. Everyone. Thanks everyone for watching. Love you.